We're going to look at proximal gradient in the dual and make connections to everything that we've done in the previous lectures in this series. So let's start at our familiar point of minimizing f of x plus g of ax, somehow our template, and the dual is maximizing minus f star of minus a transpose z, z is my dual variable, minus g star of z. And again, note that we can also think of this, we get the same solution if we look at the minimization problem of minimizing f star of minus a transpose z plus g star of z. I just took a minus sign out and took the min into the max. Of course, these have the same solution. And now z t plus 1, if I wanted to do proximal gradient, I want to use prox on g and look at and take the gradient of f, is just exactly from how we developed proximal gradient the first time we saw it. Prox of lambda g star times z t minus eta times the gradient of our function f. So I'll write parentheses to make sure clear that I haven't done the chain rule or anything like that. F star of minus a transpose z. And this is equal to prox of lambda g star of zt plus, now doing the chain rule, a times the gradient of f star of minus a transpose z. And now this is something that's familiar, so we know what this gradient is. So I'm going to call this, so this is equal to prox lambda g star of zt plus a x hat. Whoops, I need a step size. I need my step size here. And I can write this as the prox of zt plus eta x hat, where x hat is equal to the gradient of f star of minus a transpose z. And we've mentioned that this means that x hat is an element of the argmin of the Lagrangian. F of x plus z transpose ax. So now we have our basic Prox gradient algorithm in the dual, and just summarizing what's above, this is saying that x hat is equal to, I'm really just writing them just to have them together, argmin of f of x plus zt transpose ax, and then zt plus 1 is equal to prox with respect to g star of zt plus, I'm sorry, I forgot, I forgot this a, of course, has to come down here. Zt plus eta times a x hat. So this is so far so good. This is just showing what we have so far. On the other hand, now we look at this, and x hat is familiar. We get x hat by minimizing this Lagrangian, but prox maybe looks a little daunting because we now need to compute the prox operator, not of g, but the prox operator of G star. And that may be fine. If G star is something that has an easy prox operator, we can compute it. But we can also now take one more step, if it's advantageous, given the structure of our function, and use the Moreau decomposition. Recall the Moreau decomposition relates the prox operator of G to the prox operator of G star in the following way. And in particular, it says that if you can compute one, you've already computed the other. So let's recall that the Moreau decomposition says that x is equal to prox lambda h. I'm just using h as my stand-in for the function I'm using for prox, plus lambda times prox of the dual, the differential dual of x divided by lambda. And so now, just looking back at what we had, instead of the prox operator of G star, I can use the prox operator of G. So using this, I've got that zt plus 1 on the previous slide. I had written that it's equal to prox of lambda G star of zt plus lambda ax hat, where x hat solves the Lagrangian. And now, just solving for this, essentially, we get that this is equal to zt plus lambda ax hat, because the prox of the dual is equal to x minus the prox of the primal, minus lambda times prox g 1 over lambda times g, evaluated at zt over lambda plus ax hat. So now I can write this again in essentially that same form that we've been seeing. So so this is equal to zt plus lambda times ax hat minus y hat, where, just to write it again, x hat is the argmin of the Lagrangian, f of x plus zt transpose ax, and now y hat is equal to a prox operator of G. So in connection to the overall flow, we see that we're now looking at two steps. Zt is equal to lambda ax hat minus y hat. That's our update of zt, where x hat and y hat are steps that are taken using operators in the primal. So x hat is basically this is the Lagrangian on f, and y hat is given by evaluating the prox operator on G. And again, note that these are decoupled, so they're separate. They're used separately. And based on our work on the proximal point algorithm, we can write a little more carefully what y hat is. So y hat is this prox, and as always, we're gonna when trying to deal with prox, I'm gonna write out what the argument is and look at what the optimal solution is. So if y hat is equal to this prox, then y is equal to the argmin of g of y plus, this is based on all of our work on in the previous lectures in this series on the proximal point algorithm, lambda over 2 times ax hat plus zt over lambda minus y. And this is just by definition of the prox operator. Note that, why do I have this lambda on top? Usually I have 1 over twice the step size, but indeed the step is just 1 over lambda. So that comes in the numerator, and that's why I have this this lambda term there, and this is we can see that this is, I can write this separately as, or I can write this as an augmented Lagrangian term. I do that just by expanding the square and then dropping any terms that don't involve a y, since I'm interested in the argument rather than the value, our usual thing. This is equal to zt times ax hat minus y. This is again an argument over y, plus lambda over 2 times ax hat minus y squared. And so putting these three steps together, I won't write it all out, but let's see. Step 1, I compute x hat. X hat just needs to know what the previous zt was, doesn't need to know anything about y. Then step 2, I compute this augmented Lagrangian. So I should just call this is the Lagrangian. Step 2 is my augmented Lagrangian. And then step 3 is putting it all together. I'll just write it out again. It's really this term. zt plus 1 is equal to zt plus lambda ax hat minus y hat. So everything is now decoupled. So this is proximal gradient in the dual. So let's compare proximal gradient to just using prox, and again see how these compare. And basically, so what I mean by prox gradient versus PPA is we have this problem: maximize minus f star of minus A transpose z minus G star of z. Prox gradient is what we've just been working on, dealing with f and g separately. And proximal point algorithm is just simply writing zt plus 1 is equal to the prox of lambda of this entire function. That's up here, of zt. This was basically the subject of the previous two lectures in this series, and we saw that proximal point algorithm gets x hat y hat is equal to the argument of f of x plus g of y. This is an argument over x and y, plus z transpose ax minus y plus lambda over 2 ax minus y squared. And zt plus 1 is equal to zt plus lambda times ax hat minus y hat. And versus Prox Grad, zt plus 1 is, Prox Grad tells us that x hat, I'm just basically copying from the previous slide, argument over x of f of x plus z transpose ax. Y hat, we had it from on the previous slide, is equal to argument of g of y plus this term. Note that I could even just drop the ax hat in this in the first part, but I'll keep it. Is the argument over y of g of y plus z transpose ax hat. Ax hat comes from the previous from this previous step just above, minus y plus lambda over 2 times ax hat minus y, and then zt plus 1 is exactly the same. Zt plus 1 is zt plus lambda of ax hat minus y hat. So what are the differences here? The key difference, of course, is that proximal point algorithm does not decompose. So whereas proximal gradient, I get to evaluate x hat separately, and I get to enjoy any decomposition properties that f has. And also I just don't have to worry about g. And then y hat, I solve only over y. So x hat is now given to me, it's fixed. And I solve the augmented Lagrangian problem over this. So why don't we always use proximal gradient in the dual? Why would we ever think about using the proximal point algorithm? The key point is that this, we've made no assumptions. No assumptions on f, whereas really in this setting here, this especially makes sense. I'm not going to say we need, because it's not that this doesn't go through if we don't have strong convexity, but this makes sense when f is strongly convex. And again, the reason I'm saying this is that we're taking a gradient step with respect to f star, and therefore we want f star to be smooth. And another way to think again about augmented Lagrangian is that it's adding the strong convexity in the primal, or it's smoothing the dual. So this is a comparison between proximal gradient and the proximal point algorithm. And we can also, exactly in the same way, think about accelerated methods. Again, either for proximal point or for proximal gradient in the dual. Notice that this is really implementing exactly what we had before. What do you need to implement? Accelerated proximal gradient? You're basically keeping track of your trajectory. We're already doing that because we need to add that momentum term, and you're only computing gradients with respect to f, your smooth function. And computing gradients with respect to f is going to just amount to this this Lagrangian step, not augmented Lagrangian step. So it's really it's implemented exactly as above, since we need a momentum term, which again is easy from a computational perspective since we're anyway computing the trajectory. And still only involves taking gradients of f star, which correspond to partial Lagrangian minimization. And by partial, I just mean only over x. And then the Prox term is essentially going to be the same. So we can use accelerated methods as well. So let's look at another comparison with augmented Lagrangian in the setting where we have some kind of separable structure. So I'm going to write down essentially the same problem that we've been looking at, but again, more explicitly write down a separable structure for f. So I'm now minimizing f1 of x1 plus f2 of x2. Before I was generally treating this as f of x. Plus my g function, which again is going to be g of a1 x1 plus a2 x2. So this also has separable structure. But of course, if you just write g of a of x, and x is into blocks, then you can always write it like this. So this is really not any assumption on g. And the dual is maximize minus f1 star of minus a1 transpose z minus f2 star of minus a2 transpose z minus g star of z. So now let's write down what our algorithms are. We don't have to derive them again. What is a proximal gradient descent? Is, if you want to put in the details, I really encourage you to go back and do all of these calculations. But at least the form should now be something that that we expect. So if we're going to do proximal gradient ascent, and we're going to assume that f1 and f2 are strongly convex, so that f1 star and f2 star are smooth, then what do we roughly expect this to look like? zt plus 1 is going to be prox with respect to g star of zt minus plus, because we're doing gradient ascent, zt plus lambda times gradient of f1 star plus gradient of f2 star. Then we're going to recognize that gradient of f1 star and gradient of f2 star just amount to x1 hat and x2 hat, where those are minimizations of the Lagrangian function. And then instead of prox g star, I can do z plus prox g. This is kind of the flow of what we've seen so far in this lecture. So I'm not going to rederive all that again. Basically, proximal gradient ascent, putting those steps together, would give us x1 hat would give us the following algorithm. x1 hat is equal to argmin of f1 of x1 plus z transpose a1 of x1. x2 hat is essentially the same thing. Note that these are now totally decoupled, can be solved in parallel. Z transpose a2 x2. And zt plus 1, I'm either going to write this as prox lambda g star of what I have above, or use the Moreau decomposition. So in both of these forms, it's either going to be prox of lambda g star of zt plus lambda of a1 x1 hat plus a2 x2 hat, or using the Moreau decomposition, this becomes what we just derived. Zt plus lambda of a1 x1 hat plus a2 x2 hat minus y hat, where y hat is equal to the prox with respect to 1 over lambda of g, not g star, of zt over lambda plus a1 x1 hat plus a2 x2 hat. If I were to move this up here, I would have, you compute x1 hat, you compute x2 hat, totally decoupled. You compute y hat. This only involves a prox operator with respect to g. You're only looking at an x1 and x2 hat are now fixed, and then zt is this update. So we see that this has this alternating minimization flavor already. But what does this require? Again, require in the same sense of what we talked about in the previous slides. So this requires, for it to make sense, that f1 star and f2 star are smooth. In other words, I need f1 and f2 to each be strongly convex. And of course, throughout, as whenever we're talking about a proximal gradient or a proximal point algorithm, I need to assume that my prox operator on G is I can evaluate it in a reasonable amount of time. So let's now look at an intermediate regime where only F1 star is smooth. So suppose that I don't have strong convexity of F2. So what would we do? So again, my dual problem is max minus F1 star of minus A1 transpose Z minus F2 star of minus A2 transpose Z minus G star of Z. And let's suppose that this is smooth. In other words, F1 is strongly convex, but that's it. So now I can think about doing Prox Grad, but do a different split. Instead of doing Prox with respect to G star, let's do Prox with respect to this. So I will now use Prox of this sum rather than just the Prox of G. And so we'll see that that we're going to that if we so let me write this as an exercise for you. Just again, we've seen variants of this so many times that it's probably getting familiar. But just to be able to derive it is a good exercise. So if we let h of z be this composition here, I'll take out the minus. I'll leave out the minus sign. So if h of z, if I define that as F2 star of minus A2 transpose Z plus G star of Z, then the prox of H is equal to Z plus lambda of AX2 hat minus Y hat. Note that in order to get this, I've used, well, I'll let you do this exercise. We've done it explicitly in previous lectures in this series, where x2 hat and y hat is a solution to the augmented Lagrangian problem over F2 and G coupled by the norm term. Argmin over x2 and y of F2. Again, F1 is absent because we're treating that differently. We're doing proximal gradient. Plus G of y plus ZT transpose A2x2 minus y plus the augmented Lagrangian term, lambda over 2 times A2x2 minus y squared. So dual Prox Grad, in this case, becomes a combination of what we had before. Instead of doing these separable, separately doing a Lagrangian step for a Lagrangian calculation to get x1 hat, a Lagrangian calculation to do x2 hat, and an augmented Lagrangian calculation to do minimization to get y hat, we now have a Lagrangian minimization to get x1 hat, f1 of x1 plus zt transpose a1 x1, and then x2 hat y hat is the argmin of what we saw above, so I won't write it. And then finally zt plus 1 is our familiar form that we get regardless of how the x hats and the y hats are computed. Zt plus 1, zt plus lambda times a1 x1 hat plus a2 x2 hat minus y hat. So this is a detailed comparison between dual Prox Grad and proximal point algorithm. The next thing we're going to do is see a couple examples of what this looks like. So see this in action.